this, no, that's not true. A little problem. What? Another dumb question. What's the speed of sound in water? What's the speed of sound in water? Three. Yeah, but what are the units? Oh, that's a problem. Would you be comfortable with the statement that it was 4,000 feet per second? Because it is. When I just finished my acid job, what was I doing? Well, I was over in the doghouse drinking a glass of water. No, that's not what I meant. In the well, I just finished the acid job. That acid job pumped. I've got a liquid-filled system, don't I? And in that system, if I were to induce a pressure wave, sorry. You should know by now. Pressure wave, yeah. I open the valve, or I close it, or whatever. I induce a pressure wave into that liquid-filled system. How soon is the pressure wave going to be on the rock? Literally 2 or 3 seconds. Oh, but instantaneously. I have, and I got to tell you, back in the day, I had this mental picture that pressure changes at surface took long periods of time, hours, days maybe, to get, and it's not true. In a liquid-filled system, because it is so incompressible, that incompressibility means that the speed of sound, the speed with which a pressure wave moves, a P wave specifically, moves through that system, because water doesn't support an S wave. Not that that matters to you. Anyway, that P wave moves through that. That P wave moves through that system at 4,000, it's actually it's 4,700 feet per second. At 4,700 feet per second, that means that it's all but instantaneous. So that pressure wave does not damp. It's as sharp when it leaves the surface as when it hits the bottom. And it raises all kinds of questions about the physics of the system. So, where I was making the assertion to you before that it was a matter of wellbore to fracture to natural fracture to matrix, that's really not correct. Because some very important things happen in the time where the transients are moving in the wellbore. All right? So the transients in the wellbore, connection from surface to sand phase, or perforations, then perforations to fracture, induced fracture. Now that raises a point. When you do an acid job, most of you have conclusions, I assume, or certainly you're familiar with them, at least in a passing sort of way. Why do we spend all the money to buy acid? What's the purpose of the acid job? Well, when I do a build-up, most of the build-up analysis, I ignore that early time data, arguing it's wellbore storage, temperature effects, liquid, what the hell, wait a minute. There's useful signature in that data. It's just that I'm not smart enough to take advantage of using it. Okay, anyway, let's wrestle with it. Let's go forward. So I looked at middle time. I now have the matrix doing its thing. Then I have the boundary response as it hits the boundaries. And finally, I'm looking at this late time signature. I've introduced the idea that if I introduce a new transient, change the rate, change the pressure, whatever, I can start this whole path all over again. And that new transient will go through every one of those phases. And they do. And that's incredibly useful because I get to see the system as it ages. All right? And there's that efficiency term that we talked about. I want to present this graphically. And this is one of the reasons I have a real problem with numerical simulation, because when I do numerical simulation, I virtually never present the data in the way that the theory says I should make my comparisons. Not one of the simulators I know of does that. So one of the pieces I want to look for is this idea of pattern recognition. There's the pattern I'm looking for. Whoa. Dang it. If the pattern I seek happens to be a straight line, man, I can spot straight lines all over the place. Wow. Look at all those straight lines. Ooh, there's a, that really makes my problem very simple. It really does. It makes my problem so simple because all of a sudden I have reason to believe that if, operative word, 72 pica, 72 point text, bold, underlined, italics, whatever else, that if my system is behaving consistent with the theory, then it will exhibit a straight line. When, because it almost never, when it does not generate a straight line, that's when my engineering task kicks in. I now have the task of trying to figure out why did that system, which I know follows the same physics, the laws of physics are the same. They didn't change. Just because the wells in Texas does not qualify to have a different set of physics. The laws of physics are the same in Texas as New Mexico, as in France. I know the Frenchmen and the Texans disagree with that statement, but it's true. They don't have to agree with me. There's no obligation. That's okay. But it is my opinion that the laws of physics in all of those places are the same. Therefore, if the well were behaving consistently with the theory, it would generate a straight line when I present the data correctly. Virtually never do they. And so the task I have, I know exactly what I'm looking for, and I can spot it. I'm looking for a straight line. When it fails to give me a straight line, I now have embarked upon my journey to try to understand why. All right? So, part of that is the ability to discern noise versus signal. There's a very important concept. I use the acronym RPSA. RPSA. Zuna. R. Repeatability. Repeatability implies precision. Okay? So if I can measure the same thing 14 times in a row and get the same number, that's repeatability. That means that my measurement capability is precise. Doesn't mean it's accurate. It means it's precise. If it is systematic, then it is accurate. So I have two different concepts I need to wrestle with. When I am measuring data, this idea of noise versus signal, data which is repeatable is precise, but it may not be accurate because my systematic ability to measure is not good. Okay? Why would that matter? Well, for example, I'm doing a bunch of work now, and it's really a hoot. If you go look in the literature, Roland Horn out at USC, Roland Horn has, well, he was a distinguished lecturer and got a lot of press for it, good work. We're now developing a lot of electronic measurement techniques, the ability to record very high time resolution data. You're going to be confronted with this, I guarantee it. But this idea of repeatability and systematic behavior is really an important concept because what I run into, this one data set I'm looking at has got great repeatability. I mean, they are able to measure 3-second data and get the same number for thousands. Well, the data set right now is, well, as of today, the data set's 1.8 million data points. It's big. Repeatability is excellent. I discovered the other day that on an 8-hour basis, this sounds stupid, it kind of is. On an 8-hour basis, they have a systematic error that measures the hourly water rate within plus or minus 1 barrel. Hey, wait a minute. Every 8 hours, they could have made an error as much as 3 barrels plus or minus. Well, so in that 8 hours, so each hour, translated to a day, 24 hours of a day, if they made the same maximum error every hour, 3 times 24, that's 72 barrels. They would have made 72 barrel error in their liquid volume measurement because of the way they're converting their analog to digital signature. Yeah, goofy stuff like that, but it really does, and this is why this issue about noise to signal becomes a matter. Repeatability and systematic error. They get great repeatability and crappy systematic error. So their accuracy is junk, their precision is great. But it really goes to the heart of this ability to spot noise and signal. I know that my signal should satisfy that straight line. So unless I've got a process error, systematic error, I know what I'm looking for. I can also observe variations in the noise. You probably haven't gotten this far yet, but at some point in your career, you're going to cross the bridge about multiphase flow and pipes. The work that Ansari and Brill and Brown and Manami, et cetera, Duckler, Guns and Ross, you're going to cross that bridge. And that's a very useful bridge, but it's a kind of a dangerous bridge too. Because what you will see is changes in the noise that are caused by the change in flow behavior in the wellbore. Ooh, yep. The noise created by flow by heads versus the transition to bubble flow, to mist flow, what have you, becomes part of the signal. And then you get to see events in well history. I'll tell you very quickly, I'll not go into the blood, guts, and chicken feathers of it. I had the privilege of a government operation in a faraway place had invited me to come see why the reservoir system was failing so badly, because it was a disaster. We looked at the production histories and saw that the production histories were stair steps. Here it was, here it was, here it was, here it was. No, that's not right. The physical systems are reasonably continuous. They don't have stair steps in them. And I happened to notice that this happened on a 28-day cycle. Yeah, really, come on, 28-day cycle. Well, that's the phase of the moon. And I encouraged my friend, the Minister of Energy, how about you have some people with night vision goggles go out the next time there's a new moon and just watch. Lo and behold, there were folks who were showing up with tank trucks. They were smart enough to know that if they cut all of the production out, that things bad would happen, it would be obvious. So what they were doing was they were going around this field to the different tank batteries, diverting the flow, coming over with tank trucks into their batteries, hauling the production away. And it was all about theft. It turned out, looking for the signature, looking for these events, I knew that that equation was what drove the system. And it's a smooth, straight line. The data was these stair steps, and that didn't make sense. And then the 28 days, and then they discovered that that 28 days tied to the dark of the moon, and the rest was history. And the good news was, all of a sudden, by simply building a fence that you couldn't knock down with a truck, the production rate improved. How cool? How cool is that? Pretty cool. They were pleased. Anyway, I'll be careful with this list because this list in your notes goes through craftsman's prejudice about why you don't do build-ups, because I have become firmly convinced that I can learn everything that you want to do from a build-up with production data that has been recorded with the same degree of diligence. I know you're taking a well testing class, and well testing class's intent is to teach you to do the interpretation of shut-in data. Except your faculty was brave and kind enough to let somebody come in and speak heresy to you. Because in a grand sense, I am. Well, this is just a list of the reasons why production data I think is useful. And like I said, I'm using data sets now that are recorded on the 3-second interval. And there's signature in there that just would blow your mind. I mean, when the data is good. Unfortunately, I discovered that 1 second data is bad. But this high resolution data has got information in it that just, one of my clients actually discovered that changing the choke, and an adjustable choke comes normally in a 64th inch setting step, and goes 1/64th inch for each choke. They discovered that by changing the choke a 64th was enough to cause damage. And the way they found it out was looking at this, in their case they were looking at 10-second data. But they could spot the event of the choke change and immediately see the impact on the well's performance. And so all of a sudden you start looking at these production signatures and we're seeing stuff that we never even thought we could see before. Anyway, that's a short list of sales points. So you can read it and kind of move on. Wellbore storage. I already started that argument a while ago about the fact that I can shut the master valve in and the rate still continues to move at the reservoir. I need to wrestle with that. All of our literature is driven by this relationship. Every one of the papers that talks about wellbore storage still uses the original classic definition that Van Everingen and Hurst came up with. It simply says the volume of the system, whatever part of the system, your fluid level or the actual gas volume, is a function of pressure, and that relationship is a constant through time. Well, that's fine, except that unfortunately, I used to work for a pipeline company. Back in a prior life, I worked for Panhandle Eastern Pipeline. Well, one of the things I should have given you as a disclaimer at the outset, every major company for whom I worked no longer exists. I worked for Texaco, they're gone. I worked for Gulf, they're gone. I worked for Pan American, they're gone. I worked for...
That's a bad one.
It's a bad sign. I must have really screwed them up.
That's it.
What can I say? I should sit down and shut up, huh? Anyway, my job at Panhandle as a pilot company, the chief engineer, was really simple. In fact, my performance appraisals every year were simple. Panhandle, their primary client was the city of Detroit. And my job was to have no days in which we had a deficiency of natural gas to the city gate of Detroit. It was that simple. Therefore, my performance appraisal was, any day we had a volume shortage at the city gate to Detroit, Crafton's performance appraisal took a hit. Pretty simple, because we could calculate how much deficiency there was, and the smaller I could make the number, the better my performance was. I learned that this equation describes that, not this one. I was looking at wellbore storage of a 1,000-mile long, 36-inch diameter wellbore that happened to be laying down instead of standing up. But it's exactly the same physics. When I shut the well in, I get wellbore storage, and the pressure in here rises. When the city of Detroit quits using natural gas, like in the summer, that valve gets restricted, it gets smaller, it gets shut in, and the pressure in the system builds up. In the wintertime, when the city of Detroit opens that valve wide open, this system depletes itself very rapidly, controlled by whichever is the constraint. In the wintertime, that valve is the constraint. In the summertime, the reservoir is the constraint. That analogy works exactly for what we would refer to as wellbore storage and well testing. I can shut the master valve in very quickly. I can open it very quickly. I have no ability to control the speed with which the reservoir delivers fluid to the wellbore. That is the constraint. So, when I shut the valve in, storage is driven by the ease with which flow occurs into the wellbore. The same problem I had with the city of Detroit. Once the storage volume is built up, the speed with which I open that valve governs how fast I deplete this system. Speed of sound in water is 4,000 feet. Speed of sound in gas, that's roughly 600 miles an hour. So I'm looking at the scenario. Wellbore storage might literally take days when I shut the valve in, and seconds when I open it back up. You see that? So the physics of the system is driven by which end is the constraint. Is the high conductivity, or the low conductivity, or the high conductivity end of the system the constraint? If the low conductivity end is the constraint, then it's going to be slow. If the high conductivity end is the constraint, it's going to be fast. So when I'm looking at production data, where this is the constraint, wellbore storage is not usually a phenomenon that is of great importance. The signal is there, it's just hard to see. So, what are we going to do with this idea? The theory says that we should use this delta P over Q rho idea, that right there. It improves the resolution, because ARC wasn't right. It's a lot faster than numerical simulation, and it gives us a whole different way of looking at the data. Plus, we have a yardstick. We would expect it to be a straight line, and the theory is sound. Okay? So what are we going to look at? We're going to look at basically three graphs. We're going to look at what I referred to as the MDH plot, Miller-Dice-Hutchison plot. It really is exactly the Horner plot. I've taken into account superposition, all that stuff. The straight line is KH, transmissibility, if you please. presuming we know the viscosity. The intercept is the skin or the effective fracture length, what have you. On that graph, the higher up the graph you go, the greater the overhead, the greater the amount of pressure or energy consumed in the system on a continuous basis. The slope, we need to wrestle with this idea just a minute. Then the slope is either steep, which is a steep slope. A high slope implies low conductivity, low transmissibility. A shallow slope implies high transmissibility. Cartesian plot, the pseudo-steady state plot, is a measure of pore volume in the same state as true. And then the log-log type curve, there's a bunch of literature. You're going to spend some time, if you haven't already, when you go into your well testing class, you're going to be looking at the Bourdais curve, you're going to look at the Green-Garten curve, you're going to look at the actual derivative curves. Those are fine. I just found that I trust them very little. See, my numerical simulation experience, I came to know, and please take this right, because you're going to get this in the class, and you're going to okay, Crafton said this doesn't work. Well, it does work. The problem is, if you are unethical, remember my conversation with you about ethics, if you are unethical, you can get whatever answer you want. All it takes, on those derivative graphs, for example, is to use a different method to average and calculate the derivative. That's scary. Now, if you're using the same tool over and over and over, obviously that debate's off the table. Okay, you're going to use the same measuring stick for this well, and this well, and this well. You're going to wind up with a consistent analysis because you're making the same mistake repeatedly. Okay, that's fine, and that's what classic engineering method's all about. The problem is, if you said, I don't care, I'm going to just do this data set, and I'm going to find a way to get the answer you want, that's unethical in my opinion. But I can assert to you, because I've been over the road, that I can get the answer that you want because I can change the way I calculate the derivative, I can change the way I calculate the averages that generate the derivative, the list goes on. The problem I have, and that's one of the things that you'll see here in just a minute, I try to do as little processing to the data as I can, just so that I don't have that debate as an issue, all right? So just so you know, I don't really focus on the classic type curves, either the values, the curves themselves, or the derivative curves. I far prefer these other tools. And there's a paper written by Hank Rainey many years ago, actually, in which he pointed out and was arguing this very issue. He showed that, in Rainey's work, he showed that using these derivative curves and type curves actually induced more error than using the basic primitive curves. Anyway, we've already wrestled with the RPI relationship. So the reciprocal is just productivity index upside down. And in this case, it's delta P over Q, but it's really not delta P over Q. It's delta P over mass rate. All right? All of the assumptions that you've wrestled with in your well testing class, constant thickness, constant temperature, constant composition, on and on. There are 23 specific, I don't know whether you went through the derivation or not, but there are 23 specific different assumptions that you make to come up with the final equation that is the equation that we use for Horner analysis or just classic partial transient theory. So there's all kinds of them. And here's the partial list. Two of them that become a real issue is internal sources and sinks. You're going to become acquainted as you begin to dig into these resource plays, and I've heard several of you mention comments about coal bed methane. There's a huge debate in the coal bed methane community about whether or not the gas molecules are absorbed onto the clay surfaces, the shales. I don't care. Because what I have seen is, it doesn't matter. What matters is how they consume energy when they flow. But they become internal sources, and what that signature might imply. Another issue is this constant composition and isothermal. You guys are, what? How far is it from here to Roswell? 100 miles? 150 miles? Okay, Well, it would be generous to give it 200 miles. Well, I overshot. I'm an overachiever. Anyway, one of my very earliest tasks was in the Ellenberger here in New Mexico, down in that neighborhood. The company was having just screaming disasters. These were 10 million a day plus gas wells. Just fantastic. And of course, we hadn't gotten into the issue about drawdown and all that stuff. These wells would produce that 10 million a day just, wow. And then they'd do that for a week, 2 weeks, and die. Dead. You could open the master valve to the atmosphere and there was no flow. Shut the well in, leave it a week, turn it back on, 10 million a day. 10 days later, dead. Whatever. And they would repeat this cycle over and over and over again. Well, they finally got kind of crazy and said, hey, how about when it dies, we dump some alcohol down the hole? Not Jack Daniels, not Maker's Mark, just alcohol. Okay, nothing good. Son of a gun. The well came back. We then got the wild idea to run a baler. The well died, ran a baler, and we came up with gas hydrates. Snowballs, for all practical purposes. You're familiar with gas hydrates. These wells were getting so cold opposite the perforations that ice, gas hydrates were forming. That flew right in the face of our understanding about constant temperature. Because here was this wellbore exhibiting temperature depressions of around 150 degrees F. Whoa, that's not constant temperature. No, but that explained exactly what it was doing. The well would produce at very high rates, Joule Thomson cooling would cool the wellbore and the sand face and the perforations. It would get it cold enough that the hydrates could form. The hydrates started forming, which restricted it even further, which dropped the temperature even further, and we were on a slippery slope, and the well would die. It would sit there and warm back up because of the conduction of heat from the reservoir, warm it up enough that finally the hydrates would evaporate and melt, and we would suddenly see the well able to produce again. And we were just going through this ridiculous temperature cycle over and over and over again. I had occasion in the Niobrara, there in Colorado, to do some temperature buildups. Not pressure buildups, but actual temperature buildups. And what I saw was that the T stars, not P stars, the T, I hate to be under here because it creates such an echo. Maybe over here. I ought to go out in the hall, shouldn't I? That'd be weird. I can't imagine what that would be. Anyway, I was doing Horner plots with temperature instead of pressure. And what I found, they were all over the place. I could not make sense of what I was seeing with those T stars. It was just junk. Until I just happened to plot the T star change, because we knew what the initial temperature was about. So the change in temperature with this Horner temperature plot, or temperature Horner plot, the change in temperature, I got an R squared of 0.7 when I compared delta T, initial minus the T star. That delta T plotted against cumulative production got me an R squared of 0.7. Wow. I was blown away. It says our reservoir systems are not constant temperature. They're not single-phase flow. They're not homogeneous. They're not isotropic. They're not isothermal. If you look at the gas analyses from Hugoton, Kansas, which is arguably the largest U.S. gas reservoir, Hugoton, Kansas gas composition back in the early 60s, because I was taking gas samples back then. In 1961, the average gas gravity was 0.59. The average gas gravity in Hugoton, Kansas now is roughly 0.72. Wait a minute. Yeah, I know that's a long time. But it really does raise the issue. These systems, all of the classic assumptions are not correct. So what we've got to start thinking through is how would they impact this idealized signature? All right? So there's real world examples of very large systems and very large data sets. Constant thickness, no, constant, no. However, we are going to use, because it is an effective basis for comparison, this analytic solution that, if I do it correctly, should look like a straight line. All right? So, let's go there quickly. The graphical presentation. We're going to look at the type curve. It's kind of hard to see on this presentation. But this is the Agrawal and the Greengarten type curves. This is the MDH plot. That's ratios. We're going to spend some time on that. This is just the traditional arch decline curve plot. And then finally, the pseudo-steady state plot, which is once the well is in pseudo-steady state, we're down to down. So those are the kinds of graphs that we're going to pick up and wrestle with. I got 5 minutes. Got to talk a lot. Let me get you thinking this way right now, and then we'll take a break for lunch. This RBI thing, the delta P over Q rho, versus log of time. The slope, when the slope is shallow, it implies a system which has high transmissibility. Let's think about the physics of that a second. I opened the valve, pressure wave started to move. As it moved, fluid is moving from further and further and further and further away in the system, right? When it started, it was right here, in 10 minutes, and 20 minutes, and 2 weeks, and 10 years. A high transmissibility system simply says that when